So we continue with chapter number 11, part 3. So we have a surface charge and channel conductance. Okay, so we have the membrane, and in the membrane we have a channel so that the specific ion can pass through the channel and do the reaction, or helping the membrane, or helping our cell to do its function. Okay, so here we see that the conductance of ion channel varies with the concentration of fermion ion. Okay, so we have the ion channel and we have the fermion ion. Okay, so the surface charge draw ion toward the mouth of the channel, concentrating them and increasing the conductance above that expected from the bulk concentration. Okay, so we have this. So when the ion is near to the ion channel, so it can move more faster. Okay, so the concentration at the surface of the membrane plus concentration at the mouth of the channel C naught equal to this equation. C naught equal to C infinity exponential minus E var P naught over KT, and the ionic strength I equal to this equation by adding or removing an impingement ion. So the surface potential var P naught will change into this equation. Okay, so what we can say is that this, so C naught will change and alter the channel conductance. Okay, so kalau concentration banyak dekat ion channel tu, so dia lebih banyak ion akan melalui the channel. Okay, so by changing the surface potential, fermion ion can influence the flow of the fermion ion. Okay, so this one contohnya ion yang besar contohnya akan menutup ruang pada ion yang kecil untuk melalui that channel. Okay, so the example in figure 11.5. Okay, so K plus, so you can see that this one will decrease the ion formation. Okay, so this K potential, okay, so it will decrease without the impingement ion, with the impingement ion. Okay, so here the conductance of K plus a channel in heart muscle is reduced by the addition of various impingement ions such as choline, Ca2 plus and Mg2 plus. Okay, so Ca2 plus is bigger than K plus, Mg2 plus also bigger than K plus, so it will stop the K plus from entering the channel. The drop in conductance reflects the neutralization of a negative surface charge, leading to a reduction in the concentration of K plus at the mouth of the channel. Okay, so here if we have Ca2 plus and Mg2 plus at the membrane surface, so if we screen out the K plus, so K plus cannot find the channel. Okay, cannot be attracted to the channel. So as the ionic strength increase, the effect of the existing surface charge is neutralized, so the channel conductance approach the value that would be seen in a neutral membrane. Okay, so ionic strength increase, so K plus also attracted to this channel. So here if we have the concentration, initial concentration C naught equal to 2 pi sigma squared over var epsilon KT A to the 10 to the power 3. So C naught is the charge surface, so we go to a finite limit as the bulk concentration is reduced to 0. Okay, so a finite limit, so because there is a small concentration, so all the ion or all the charge is attached to the membrane surface. Okay, this means that for a channel in a charged membrane, as the fermion ion concentration is reduced, the conductance can go to the non-zero limit. Okay, so it can be macam contohnya macam pondok tool waktu waktu peak hour, bukan waktu peak hour, so the car can pass through the toll easily. Okay, kalau waktu peak hour kita akan menghadap jam contohnya. Okay, so in CA2 plus activated K plus channel experiment, the lowest conductance seen at low K plus concentration was about 30% of the highest conductance obtained with a setting K plus concentration. Okay, so low concentration, so this one can these are non-peak hour, so these are peak hour, so this one is much better flow, much better than this saturated K plus. Okay, so figure 11.6. Okay, treating the channel conductance as a saturating function of CO gave a curve that remained quite high as the concentration decreased. But as the bulk concentration fell into the low range C0 and the channel conductance also dropped sharply. Okay, so walaupun kita kata low K plus, but kalau terlalu low K, concentration of K plus is terlalu low, terlalu sikit pun the conductance also will drop sharply. Okay, because tak banyak kereta, contohnya kalau dalam tol tak banyak kereta yang lalu pada tol booth. Okay, okay, so the surface charge, so the membrane, we have the membrane, and this surface charge will influence the voltage gating. Okay, so the voltage gating of the channel, open or close. Okay, so surface potential has a direct effect on voltage gating of ion channel. So the difference between the voltage at each surface, kalau kita ada membrane, part A, compartment A, compartment B, so we have a voltage difference. So changing the surface potential at one or both sides will thus change the electric field acting on the channel. So the property of channel opening is equal to this equation. So changing the concentration of ion will affect the electrical potential var phi depending on the two sides, and delta var phi naught will change. Okay, so this one will change. So when this one will change, so the property of channel opening or close will be decreased or increased. So delta var phi naught can be addressed by adding or removing ion on just one side of the membrane. Okay, so kalau kita ambil contohnya, kalau kita ambil terlalu banyak garam, okay, apa akan jadi kepada sel-sel dalam darah kita. Okay, so let's say we have the terlalu banyak garam, Na plus NOCl, so it will do the osmosis dan sel kita akan mati contohnya kan. So monovalent ion produce shift that are in reasonable agreement with Gauss-Chapman theory, monovalent ion, and for many channel divalent cation produce variable shift, and this is the signature of Stern layer formed by specific binding. So these are many channel divalent cation. Okay, so a bigger and a stronger attachment to the membrane. So we have this property opening become small or increase. So next is the electrophoretic mobility. So if we have produce a electric field in the membrane, so we have electric field, so it will change the migration of the charged particle. So this will called is electrophoresis. So the force exerted from our EM, kalau kita tengok EM, kita ada charge, kita sediakan electric field, medan magnet or medan electric. Okay, so these are for medan electric. the force exerted by the field is F equal to E times Q. Q is total charge, E is electric field, and the resistance, frictional resistance, FF equal to minus FV. V is frictional coefficient, V is velocity of the ion. So the ion velocity changing to this, both solving these two equations, we have V equal to EQ over F. So the electrophoretic mobility, U, the ratio of the velocity to the field, U equal to V over E equal to Q over F, or in this case ion, sphere ion, Q equal to 6 pi eta A. So where A is radius of particle and eta is the viscosity. Okay, so this equation cannot be used. This equation cannot be used when ion exists in the solution, because the counter ion that are concentrated in the vicinity of the particle undergo electrophoresis in the opposite direction. So we cancel this mobility. So the movement of this ion causes the fluid to stream along, and this moving fluid pull the particle in the direction opposite to the direct pull exerted by the electric field. Okay, so lebih kuat daripada movement by the electric field. So if that, so U is much lower than that given or that is expected by our calculation. Okay, so interaction between counter ion, fluid and surface charge, figure 11.8, shear force, this equation at the steady state. So we have the Poisson equation, solving it, so we are going to get minus var epsilon 4 pi eta var P naught equal to V naught over E. Okay, so we can calculate the speed at initial value, okay, with the initial electric potential. Okay, so in Gauss-Chapman theory is the potential at distance where an ion is in direct contact with the surface. So var pi naught is the potential at this distance where the fluid stick to and move with the particle. Okay, so meaning that the ion will stick to the fluid, and or the particle, the fluid stick to the particle, or for the ion, or the membrane, or for the protein. So it will reduce the potential. So these are without any proof. The Helmholtz equation, the electrostatic mobility equation, can be written as var epsilon zeta over 4 pi eta, where zeta is zeta potential, equal to var pi naught. Okay, so it is independent of the particular way in which var p and rho vary with x. Okay, so this one is independent of this var t and rho t, or var x or rho x. Okay, so it's only consider at the starting point or at starting coordinate. So the potential at r zeta equal to, so we can calculate without any proof. So these are the potential zeta. Okay, so when r at zeta nearly equal to a, so we can simplify using the Taylor expansion. So u equal to, putting into this equation, solving this equation, so we can have u equal to q over 4 pi eta a 1 plus eta plus a divided by lambda d. Okay, so we can use this electrostatic mobility to see the movement of the charged membrane, or no, charged molecule in the membrane or the ion in the solvent. using this equation. So we have the charge, the d by length, and the radius of the macromolecule or the biomolecule. Okay, so a particle much larger than lambda d, we see how. So lambda d, so u is lower than that given by a Stokes law. For particle with size comparable to lambda d, u become less accurate. So you put into this equation. So uh, this one is equal, let's say 1 plus 1. Okay, 1 plus 1. Okay, so become less accurate. So when the particle is much larger than the thickness of the ionic, equation 11.69 in our textbook will be accurate for the electrostatic mobility. Okay, so we can estimate the mobility of that particle. Okay, so this picture is show the ship coming plus to this gate or the channel. You can see that in order to pass the gate, so only one gate, so semuanya berlumba-lumba nak masuk to pass this only one gate. Okay, so if let's say we have this one is only sheep, but kalau kita ada contohnya gajah, kerbau, lembu, semuanya, so this will affect the movement of this sheep passing through this gate, or in our problem in our ion channel. Okay, so if we have a lot more gate, so then it can this ship can move without concentrating on only one gate, but moving to another gate or passing through another gate. So that's all for chapter number 11.